All right, so we're going to be talking about lesson 911 in this section, but this is Math 2. So far in our math career in Math 1 and Math 2, we've talked about quadratic equations, exponential equations, and linear equations. So if you recall, quadratic equations are x squared. That's what we've been working with this year. Exponential equations is when you raise a number to an exponent that is a letter, like 2 to the x. So let me write that down. You can't see my face. Quadratic is like x squared. Exponential is like 2 raised to the x, or maybe 3 raised to the x. Those are exponential. And that is probably hard to see. Let me get some shape behind there so you can read that. Let's put one over here too. Okay. And then, of course, lines, linear, which we know the best, would just be x, 3x plus 5, etc. So that's linear. Okay. In this chapter, we're going to be, and all quadratic equations, by the way, are x squared. X cubed is a cubic equation. It's a different kind. So that's another family, another set of functions. We're going to be working on collecting data and writing a function to model a trend in data that we see. And so we're going to take that and generalize our results and try to come up with some predictions. So our goal today is to figure out what will the graph look like, and we want to figure out if we should connect our points or not. So if our data points should be connected or not. And so we haven't really talked about this particular idea of connectedness yet this year. So connectedness is when there's 2 reasons why we do not connect our dots. One is because the data does not have a pattern or a trend. You can't see one, so that would be your basic scatter plot. We can't really see a data trend, so we're going to not connect our dots because we don't really know what's happening. The other reason we don't connect our dots is because there's no data in between the points. Like, let's say we're talking about the money in my bank account. So in my bank account, I have $20, and then the next month I deposit $20 more, so now I have $40. At no time did I have $30 in the bank. I had 20, then I had 40. Then I spent money, and now I have $18 in the bank. But I only had these numbers at this time, and that's what it is. So that would not be connected because there's no way to say that, well, then I must have had $30 for a minute. Sorry about those announcements. I did turn off you didn't have to actually listen to them just except for the beep, so hopefully they weren't too annoying to you. But anyway, and then we're going to try to figure out which type of these 3 functions that we know best fits our data. Okay. So what will the graph look like, and how should we connect them or not? Those are our big questions. So we're going to talk about Scott. After looking in the mirror and feeling flabby, Scott decided that he needs to get in shape. He's joined a gym and added push-ups to his daily exercise routine. He started to keep track of the push-ups in this lovely bar graph. Good for Scott. He drew that pretty picture, then he got tired of drawing it. After 4 days, Scott is certain that he can continue his pattern of increasing the number of push-ups for at least a few months. Model the number of push-ups Scott will complete on any given day. We're going to do that first. On any given day. So on day 1, he completed 3. On day 2, he completed 5. On day 3, he's completed 7. And on day 4, he's completed 9. If you can, go ahead and complete that table on your own. So you might want to notice what's happening with the pattern, what's going to happen, what's the next number. If we follow this trend, maybe you notice that, oh, this is what's happening to his pattern. Okay, that's what's happening. Maybe that's what you notice. So it looks like my next number will be 11, then 13, then 15, because he's adding 2 more push-ups every day. Okay, the next thing we want to predict is the total number of push-ups in 7 days. So we want to do, on day 1, he's done 3 total push-ups. But on day 2, he's done his 5 new push-ups plus the 3 he did the day before. So now he's done 8 total push-ups. So on day 3, he's done 15 total push-ups. And on day 4, he's done 24 total push-ups. And on day 5, he's done 35 total push-ups. I'm just adding, in case you haven't caught on, I'm adding this number to that number and writing it down here. Okay, so 24 plus 11 is 35. So my next 2 numbers will be 48 and 63. Okay, and so let's predict what the graph will look like. So either the graph will be a line, or a curve. That's the first thing to think about. It's either a line or a curve. Which one do you think it is? Now, if we were talking about f of n, we are talking about total. It said total, bolded it. So we are talking about total, so we're talking about this column. Will it be a line or a curve? If we were talking about f of n, that would be a line with a slope of 2 because the rate of change is 2. But we are talking about g. So what do we think it's going to be? A line or a curve? That's your first choice. I'm going with curve. And then I have two kinds of curves I know. Exponential curves and linear curves. Not linear curves, excuse me. Our new curve that we've been working on this year, which is quadratic. Okay, so we know what quadratic curves are. We've been using them for a while. We know that they are x squared like things. X is always something's getting squared in them. That's what always happens. Which one is it? Okay, so you've made a guess. Let's take a look at next one. We're going to be putting it on Desmos. That's what it says on my next slide, is to put the data on Desmos. So I'm going to go ahead. I've got Desmos. I've already put it in. Let's just double check that. See, I've put in my total. So I've got 1, 2, 3, 4, 7. 1, 2, 3, 4, 5, 6, 7. And then I've got the numbers 3, 8, 15, 24, 35, 48, and 63 here. So let's take a look. And I can't see anything because I can't see it. So I'm going to click on the wrench and make it so I can see it. So I don't need any negative numbers. So I'm just going to go -1 to 10. I only go out to 7. That should be fine. And then I'm going to go from 0 up to, I need to go up to 63. So I'm going to go up to 70. And here are my dots. So I'm just going to, and then I'm going to go ahead and make it a little larger. Okay. And so in case you didn't know, I clicked on the wrench, I typed on here, and now I've manipulated it so it's not clean anymore, but that's how I got that. Okay. I am stepping by tens. That's why it's counting by tens up there. So from this vantage point, this does look like kind of like a line, but I did think it was curving. And if I zoom out a little bit, I can see that that's not a line. It does curve just a little. So the question then is it exponential or quadratic? Now quadratic's U-shaped and there's not a U, but exponential, it looks like this. Remember, it's 2 raised to an exponent. And so that's exponential. And see how it shoots off really fast? This doesn't seem to be shooting off at a dramatic way. And it seems like a much calmer curve, if you will. Okay? See how it's really missing? And then of course it misses a lot at the end. Okay? So I'm actually going to go back to there. That's where I want to be. Okay. So let's talk about some patterns here. So I'm just going to play some pattern games as I think about what's happening. So I'm just going to write some stuff down. It's going to be pretty random. Let's talk about doubling. So let's say I had the number 2 and I just doubled it. So I get 2, 4, 8, 16, 32, 64, 128, 256, 1024. In case you didn't notice, this is how big of a phone you can buy, you know, how much amount on your phone. Those are your number choices. I'm sure you've maybe seen that, like on an iPad if you're trying to buy a new one. Okay, and let's talk about the rate of change. How much am I adding to go from here to here? Well, I add 2. And to go from here to here, I add 4. And to go from here to here, I add 8. And to go from here to here, I add 16. And so on. I'm just adding the number I have already. Yes? Well, if I keep going in this pattern, I need to move all of my scribbling, and it's annoying. Let's actually move this. That'll be easier. Okay. If I keep going, if I did the rate of change of the rate of change, which is a strange thing to do, but bear with me, this is also +2 and +4 and +8. I actually keep getting the same thing. So the rate of change of an x, this is exponential, this is 2 raised to the x. That's what doubling means. The rate of change of an exponential equation is an exponential equation, which is strange and strange and strange. It's totally weird. That's the rate of change. So I want you to understand that it's a very strange thing, but that's what's happening. Whereas when I look at a quadratic equation, so that's my rate of change of my exponential equation. Let's just leave it there. And let's go put over here the quadratic stuff. So I'm just going to take a number and square it. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and 10 squared is 100. And I look at that rate of change. I'm adding 3, I'm adding 5, I'm adding 7, I'm adding 9, I'm adding 11, and I'm adding 13. And if you'll notice, that's this column of numbers, which is what I'm adding in this pattern, right? That's what's happening. It's the same. This is a quadratic pattern. So go ahead and take a minute and think about that. All right. So again, looking at this pattern, what you can see, how you can see this is that's the numbers we're adding as odd numbers. It's very interesting with quadratic equations. The rate of change is a line, because the rate of change of this is add 2 every time, right? Plus 2, plus 2, plus 2. So it's just a line. That's why it was so easy to build this column and a little harder to build the green one. But quadratic, that's what it is. So I believe that this is what was expected. All right, let's go to the next part. Okay. Enter the graph, we did that. So what kind of function do you think we should use to model? So we're going to use a quadratic equation. And quadratic equations are x squared. Okay. So we're going to do something with x squared. So I'm going to go ahead and take those numbers that were in my chart a minute ago and just write them down so I can think about them. So 3, 8, 15, 8, 15, 24, 35, 48, and 63. Yeah. And I'm going to put above them your basic numbers getting squared. So 1, 4, 9, 16, 25, 36, 49. Now, it's off a little bit, but if we think about it, this one kind of goes with that one because it looks a lot like x squared take away 1, right? I square a number and I take 1 away from it. These are all 1 less than a perfect square. The next number will be 64. This is 1 less than that. But that's not correct because this is the part that gets weird. I need to get the right answer. When I plug in 1, I need to get 3. And when I plug 1 into this, I get 0. Because 1 minus 1 is 0. And so that doesn't work. So I need it to be when I plug in 1, I get 3. So I'm supposed to be plugging in 1 and getting 3. I know I'm squaring something. I think I'm probably subtracting 1 from whatever I squared, because these are perfect squares, take away 1. Does that make sense? Perfect squares, take away 1. So I think I'm squaring something and taking 1 away. What am I squaring? That's the part that's weird. I need to plug in 1 and get out 3. So 1 is x. So thinking of plugging 1 in for x, I need to get out 3. Well, that means I needed to have what? This number needs to be 2. And when I plug in 1, that number needs to be 2. So what should I do to 1 to get 2? Let me do that over here. So when I plug 1 in, when my input is 1, 3 is my output. When my input is 2, 8 is my output. When my input is 3, 15 is my output. Okay? So when I plug in 1, I get out 3. That's what I'm thinking about. So when I plug in 1, I get out 3. So, because 4 squared, take away 1, that's where 3 came from. Okay? So, I think maybe I'll try adding 1 so that it works out. Let's see. So when I plug in 1, to what I've underlined, might as well just leave it there. I'm having trouble getting rid of it. When I plug in 1, I get 1 plus 1, which is 2, and 2 squared is 4, and 4 minus 1 is 3. Okay, it worked. Let's plug in 3. 3 plus 1 is 4. 4 squared is 16. 16 take away 1 is 15. Let's try this one. This is the 7th number on my list. When I plug in 7, I add 1 to it. That gives me 8 squared, which is 64. Take away 1 is 63. And that is why this is the good equation. I think that's it. Let's go ahead and go back to Desmos and type it in and see if we're right. Okay. So, y equals x, parentheses, x plus x squared minus 1, you can see is off. It's not the right set of data. Let me change that color. It's not the correct set of data. But if I add 1 first, see how it goes through every single dot? And if I don't take 1 away, see how it's just above every single dot? Okay, there we go. And that's that. That's our equation. And it looks like it matches perfectly. So that's our equation. Scott's Gym is sponsoring a Macho March promotion. The goal of Macho March is to raise money for charity by doing push-ups. Scott has decided he'd get to participate, and he has sponsors that will donate money to the charity if he can do at least 500 push-ups. And they will donate an additional $10 for every 100 push-ups he can do beyond that. Estimate the number of push-ups Scott will do in a month if he continues to increase at the rate we were noticing. So in other words, use the equation we just came up with. How many days are in a month? Well, it's Macho March. And since it's March right now, March has 31 days in it. And so if he continues at this rate, where x is the number of days, 31 plus 1 squared minus 1. 31 plus 1 is 32 squared minus 1. 32 squared is 1024. Take away 1 is 1,023. Total push-ups. Total. Not in a day. He didn't do that many in a day. That's when he did all together in March. Starting with 3, then 5 each day. Starting with that pattern of each day. Will Scott meet his goal and earn money for the charity? Sure. Yeah. Of course. Wow. Of course. Yes, he gets a bonus. How much? Well, he did 523 extra, but we'll just go with 500 extra. So that means $50 bonus. Okay, no big deal. What more can be said about the function we just used? Consider this as we answer the questions. What are the possible input and output values of Macho March? Well, the input, the domain, the only thing we can put in is the days of March, right? We have day 1 of March, day 2 of March, day 3 of March, and so on. We can't put in day 1.5. That doesn't make any sense. The range, then, is the numbers we got, which was 3 total push-ups, then 8 total push-ups, then 16 total push-ups, then 24 total push-ups, then 5 total push-ups, and so on, right? So that's his domain and range. Okay. And our equation let's go back and look at Desmos. That equation We can put in negative numbers. We get out negative push-ups for day -1. Does negative number of push-ups? What? Yeah, he does negative number of push-ups. That's ridiculous. I've never done a negative push-up. So they're very different. Sorry. They're very different and very different data models. And so that's important to notice. So our data is only good when x is greater than or equal to 1 and a whole number. Officially, our data is going to be discrete. They're not connected. There's nothing in between day 1 and day 2. There's no time. I mean, yes, he did 5 push-ups at some point, but there's no time when his total was 5. His total was never 5. That makes sense. So we would consider this a discrete function. And that's it. That's all we're going to talk about today. There's one more question on this worksheet which I'm not going to get to, and that's it. Have a great day. I'll see you guys later.